Okay, so this PT video is on the EM spectrum, the electromagnetic spectrum, and the uses, risks, and sort of descriptions of explanations of how those uses work. So the first thing we need to be clear about is the order of the parts of the spectrum. And the idea that this is an artificial division. Human beings have decided to divide these things up into these names. The electromagnetic waves in this spectrum are all very, very similar. They're all the same phenomenon. We just give them these names because they interact with materials differently, and so it's convenient to give them these names. Okay, so you need to remember the order. One way to do it, if you have trouble, is a mnemonic. Something like Ronald McDonald in Venice uses extra garlic, where the first letter of the mnemonic matches the first letter of the part of the spectrum. You can make your own one up if it makes it easy for you to remember, but that's just something to bear in mind if you do have a struggle with remembering the order. And you also need to know which end is which in terms of three quantities. You need to know that the radio end of the spectrum is the long wavelength, low frequency, low energy. So that's relatively straightforward to remember because it's all the L's. Long, low, low. Long wavelength, low frequency, low energy. And that gamma is therefore the opposite end of the spectrum. I've put sort of the range of wavelengths on there, although it's probably not necessary for you to know that. If you've learned everything else, then by all means put that piece of information in your head. You just really need to know that radio is long wave and gamma is very short wavelength. You also need to know and remember this number, that all types of wave in the EM spectrum travel at 300 million meters per second, sometimes written as 300,000 kilometers per second, in a vacuum. Okay, so through space. They will be going at different speeds if they are going through a different material. So going through glass or water, they will be slower than that. Okay. Other thing to remember is that they can give you the spectrum either way round. So I've just flipped it round. There are often some questions, especially in the foundation paper, where it's just fill in the gaps in the spectrum. You must make sure you're clear on which way round it is before you start doing that. Don't just learn the order and blindly apply it. Make sure you're looking. You don't just write microwaves in the box that's one from the right because it's always microwaves there. It's not. It could be either way round, so make sure you've got it sorted. The other things that you need to know is the order of the colours in the visible part of the spectrum. Obviously, red is next to infrared, and it goes orange, yellow, green, blue, indigo, violet, though both of those are basically purple. And again, if you want a mnemonic to remember that, then Richard of York gave battle in vain is the standard one. And obviously, if the whole spectrum flips, then the order of those colours flip as well. So make sure you've got violet next to ultraviolet and red next to infrared. Okay, so that's the basic layout of the spectrum. Worth bearing in mind as well, if you've watched the photon video, that when it says high energy for the gamma rays, it's referring to the energy of an individual photon. So a gamma ray photon has extremely high energy, and a radio photon has extremely low energy. Okay, so we're going to go through each type of radiation in turn and just briefly discuss the uses, the risks, and give an example of explaining a use by using the sort of radiation journeys model of radiation with certain keywords that I'll point out as we go. So radio waves, TV, radio signals, obviously, communications in general. There are no serious risks from radio waves that we know of, largely because their photon energy is so tiny. So an example of an explanation, a radio transmission. A radio wave would be emitted by a radio mast, transmitted through the air, because the air is transparent to radio waves, that means it lets them through. And when the radio waves reach a radio aerial, say attached to a radio in your kitchen, they are absorbed, and that's what transfers the signal. Okay, so when you're doing these descriptions of how these applications work, make sure you're using the keywords. So emitted, transmitted here. There's also reflected and absorbed. Those four words, emitted, transmitted, reflected, absorbed, are the critical ones to try and use. Try to avoid saying things like given out by and travels through instead, because there are often marks in the mark scheme specifically for those words. Okay, so try and keep an eye out for those as we go through other uses. Microwaves, again, we talked about the fact that the microwave photons are very low energy, so radio waves and microwaves both non-ionizing. There will be another video discussing the difference between ionizing and non-ionizing absorption if you need that clarified. The basic idea is that non-ionizing radiation can't remove electrons or break chemical bonds, so its damage tends to be from heating effects, as you can see here. We know uses of microwaves, mobile phones, heating food, and satellite communications. Use microwaves rather than radio waves for satellite communications because radio waves tend to be reflected by the upper atmosphere, so they wouldn't be able to get through to the satellites. And the risks here, internal heating of the body. This is really only for microwaves that are the very specific sort of frequencies used in a microwave oven. Those are designed so that the microwave radiation makes water molecules rotate and transfer as energy to them very quickly. That's why microwaves heat the water up in food so well. There have been concerns about the microwaves from mobile phones, which are a different part of the microwave region of the spectrum, doing a similar thing. The power output from phones is so low, and it's the wrong wavelength of microwaves, that lots of studies have now shown that that risk is very, very, very small, if there at all. Okay, so example of the microwave oven. This is the one that's specifically mentioned in the syllabus you need to know. Microwaves emitted from a source inside the microwave oven. The metal walls and the grill in the door reflect the microwaves, and the water in the food absorbs the microwaves. And this absorption transfers energy to the food. If you remember that all waves transfer energy, electromagnetic waves included, so that's what heats the food up. Interesting other little points to note here, of course, is that the door reflects microwaves, but the reason it's a grill is so that you can actually see inside the oven. So that door is reflecting microwaves, but transmitting visible light at the same time. So we can see that different materials will affect the different parts of the spectrum in different ways. Okay, so infrared, next one, a bit faster through this one. Bunch of uses there. Thermogram is just basically an image where we can tell what the temperature of something is by using the infrared emitted from it. Okay. Risks here, heating effects again, and burns. Infrared tends to be absorbed in very thin layers in the surface of things rather than microwaves that penetrate through. So burning to the skin is probably more of a risk for infrared than it is for microwaves. Okay, so an optical fibre is one example of this, used to transmit information. Infrared or visible light can be used for optical fibres. Again, the glass and the plastic is transparent, so the light is transmitted down the fibre. The interesting thing that happens here is where the light reaches the edge of the fibre, it's reflected back into it at the boundary between the glass or plastic and the air. And that's what keeps the signal contained within the fibre. So this links to the idea of digital transmission. So if you want to go and look at the digital and analog video in P2 as well, that'll explain that in more detail. Okay, visible light. Well, obvious uses here. Human vision is a big one. DVDs use red laser diode and Blu-rays a blue one, unsurprisingly. And the major risks here are eye damage. If you look into too bright a light source, for example the sun, then when your lens concentrates the energy at your retina, it could cause damage. So how does human vision work, for example? Well, sunlight is reflected from objects, so we can't see the objects in the world, most of them, because they give out their own light. They're not luminous. They can only be seen because light is reflected. Same sort of thing with the moon. The moon can be seen in the night sky because sunlight is reflecting from it. Some of this light is transmitted through the air into our eyes. The lens focuses the light onto the retina where it's absorbed. Important to note here that if you want to detect radiation, you have to absorb it. So the retina is a detector. It tells us where the radiation is coming from and what sort of radiation it is, what colour. And in order to do that, it needs to be absorbed. Okay, so that's visible. We said non-ionising for visible as well. The visible region of the spectrum is really where the sort of crossover happens between ionising and non-ionising. The main reason being that, of course, if we talk about ionising as being able to break chemical bonds, then not all chemical bonds are identical. If you have a very weak chemical bond, you do not need a very high energy photon to break it. And so there's not a clear dividing line between ionising and non-ionising, and some visible light photons will ionise and be able to break certain chemical bonds if they are weak ones. Okay, ultraviolet, usually regarded as ionising. Main uses, detecting forged banknotes, tanning and vitamin D synthesis in the skin. That means your skin can make vitamin D if it's exposed to ultraviolet light. The main risks here, sunburn, cataracts, which is basically where you form an opaque layer on your eye and you can't see through it. And skin cancer from DNA mutation. Only skin cancer because the ultraviolet cannot penetrate very far into the skin. It's mostly absorbed in the surface layers. So banknote fraud is an interesting example here. How's the UV used to detect it? Well, in dark places where you can't really hold up the banknote to the light to see the watermark in the middle, you often have a UV light and you hold the banknote underneath it. and that UV light emits UV radiation, which is absorbed by the banknote. An interesting point here about how this works is that we need to be able to see the photons coming from the banknote to see if it's real. And obviously, if it just reflected the UV photons, then we wouldn't be able to see them. So what the special fluorescent ink in the banknote does is it absorbs the energy from the UV photon and then converts that into photons of visible light. So it takes the large chunk of energy from the ultraviolet photon and splits it into smaller packets of energy that are visible light photons. And then we can see those by absorbing them in our retinas again. So the ink appears to glow, but only when you put it under the ultraviolet light. And it's very difficult to make that ink and to put it into the banknote in the right way. So forgeries can be easily detected. Okay, X-rays. Everybody knows at least one example of X-rays. Try not to say X-ray as a use of X-ray. You need to be clear. So imaging the skeleton makes it clear that you know what you mean. CT scan is just a sort of fancier version of an X-ray, which can build up a 3D picture by taking lots of different X-rays of the patient. It's used for scanning luggage in airports, and and gamma rays for detecting cracks in pipes. The main risks here are increased risk of cancer inside the body because the X-rays can mostly penetrate through the body. So how does a medical X-ray work? Well, again, you have a source of X-rays that emits the X-rays. And the difference here, again, is the difference between how the materials behave with the X-ray part of the spectrum. The soft tissue in the body is mostly transparent to the X-rays, so it transmits them. That's why you can really see the sort of faint outline of the flesh on an X-ray picture. The bones, however, because they've got heavier elements in them, like calcium, are opaque to the X-rays. That means that the X-rays can't get through them, and so they're absorbed. And if you place an X-ray film behind, say, a patient's arm, if they're having an X-ray, then basically what you get is a shadow image of the bones. So in the same way as if you hold up an object in front of sunlight, you'll get a shadow on the wall. If you hold up bones in between the X-ray source and the film, then you will get a shadow of that bone on the X-ray film. And the X-ray film will change in the regions where it receives the X-rays, and so you'll be able to see that outline. Okay. And the final part of the spectrum, gamma, which again is highly ionizing, used to sterilize surgical equipment and for medical imaging, where you inject radioactive traces inside a person's body, and also for cancer treatment. Now, this is interesting because people say, well, how come if one of the risks of gamma radiation is that you will develop cancers, why is it used for cancer treatment? And it's all to do with dose. If you have a really high dose of radiation, then you can actually completely kill a cancer cell. Whereas if you have a lower dose, you have a risk of mutating normal cells and turning them into cancer cells. So what you want to do is to have all the radiation dose concentrated at the tumour site and very, very low dose, so the risk of causing further cancers is reduced everywhere else. Okay, so what they do is they have a narrow beam of gamma rays, either multiple beams coming from all directions, or they rotate either the beam or the patient, so that the gamma rays only pass through the tumour at all times, and that means it absorbs a large dose, and the rest of the dose is kind of shared throughout the tissues of the body, so no other tissue really gets enough of a dose to cause a significant increased risk of cancer. So there's uses and hazards. The uses and risks things are the most important things for you to learn. The yellow boxes are the examples. It's useful to know them, but I don't think it's worth necessarily learning all of them. The microwave one is the most important one because it is specifically mentioned on the syllabus, and then probably after that how the X-ray machine works. Hopefully that's given you a good overview of the spectrum, and again, more detail on ionizing and non-ionizing radiation in a later video.